Now we're going to say a few words about crystal imperfections. As I said at the beginning of this course, we are going to consider this periodic repetition of atoms in crystals, and then we will add imperfections as perturbations. So that's how we build up the theory of solid-state physics. So what are these crystal imperfections? These are deviations from the ideal lattice structures that are known as defects, and we can basically group them as zero-dimensional, one-dimensional, two-dimensional, and three-dimensional defects. Zero-dimensional defects are also known as point defects. The first one is a vacancy. A vacancy is an empty lattice point. As you can see here, when we have an empty lattice point, so there is this periodic arrangement of atoms, but one of them is missing. It's called a vacancy. It's a zero-dimensional point defect. Schottky defects, on the other hand, are vacancies that are created by the ion moving to the surface. So here is the example. You have the crystal surface here on the top, and here's an atom that moved from its lattice point position to the surface, creating a Schottky defect. Interstitials are atoms placed out of lattice points. These could be self-interstitials, or it could be interstitials created by impurities. So you have a self-interstitial here that is basically at a point that it is not supposed to be. So here's an interstitial. You can see the atom is placed in between lattice points and basically it's not where it's supposed to be. Impurities are different types of atoms at a lattice site or as an interstitial. So we have in the host material we have a foreign object, an impurity, that has misplaced one of the atoms and has replaced it. So this could be at a lattice site, or it could be as an interstitial. On the other hand, we also have Frankel defects. Frankel defects are vacancy interstitial pairs. You can see that an atom has been misplaced and has left behind a vacancy, so this creates an interstitial vacancy pair. That's called a Frankel defect. Okay, so if an atom moves from a lattice site to a point between lattice sites, an interstitial vacancy pair is created. Such a defect is known as a Frankel defect. Okay, so what do these point defects do for us? They affect the crystal pattern over several interatomic distances. So they have an effect over several atomic distances, interatomic distances. A vacancy relaxes neighboring atoms. Interstitials push the neighboring atoms. So you can see here there's an empty space created, so the atoms can relax a little bit, so they can move basically towards this vacancy and they can relax. On the other hand, when we have this interstitial here, this is going to push the atoms away from their equilibrium lattice point positions. Okay, so it has this effect. Vacancies and interstitials, so for example, Frankel defects here, are created thermally generated. In thermal equilibrium, we should have a certain number of vacancies, a vacancy concentration in the solid, and this is the idea is to increase entropy. Okay, so in thermal equilibrium, a certain number of vacancies is always present to increase entropy. The probability that a given site is vacant is proportional to e to the minus ev over kt, because you can think of this lattice point as in thermal contact with the rest of the heat reservoir created by the rest of the solid, the atoms. It obeys the canonical distribution, and ev is the energy required to move an atom from a lattice site to the surface, and it's of the order of 1 electron volts, and for a 1000 Kelvin temperature you see that one expects to have an equilibrium concentration of 10 to minus 5 vacancies per per volume. Roughly the number of vacancies is 10 to minus 5. That's a rough number. And as for the linear defects, one-dimensional defects, we have dislocations. When there is an extra plane added, you can see here we form a line, and this is basically our dislocation. It's called edge dislocation. On the other hand, if a plane moves up, we have what is called a screw dislocation. You can see here it's turning like a screw, so you have an extra plane moved up and therefore created a terrace with the neighboring plane, and the terrace gets narrower and narrower as we go into the solid, so this is called a screw dislocation. Two-dimensional defects are surfaces, basically just the fact that your crystal is finite, it has an imperfection, the surface is itself a two-dimensional defect. On the other hand, in polycrystalline samples we have grain boundaries, so that's where the orientation of the atoms changes. So these grain boundaries are basically two-dimensional defects, and we also have twin boundaries, which is also a type of grain boundary. We could also talk about tilt boundaries, etc., but those are details. Really, they all fall into the category of grain boundaries in polycrystalline samples. On the other hand, for three-dimensional defects, volume defects, we have voids. So if you have a cluster of vacancies, so you have a three-dimensional vacancy created in the solid, it's called a void. We can have a group of defects, dislocations, vacancies, etc., forming a crack in the material. We can have stacking faults, so we talked about stacking in hexagonal close-packed structure and face-centered cubic structure. For example, in face-centered cubic structure, the proper stacking is ABC, ABC, but here you can see that I have ABA. So this is not the proper stacking, so we have a stacking fault. So that creates a three-dimensional defect. Okay, so in summary, we have point defects, vacancies, interstitials, impurities. Schottky defect, if it's an interstitial vacancy, it's a vacancy and the corresponding atom has moved to the surface. Frankel defect is an interstitial vacancy pair. There is an equilibrium number of vacancies in a solid to increase entropy, which is determined by the energy required to move the atom from the lattice side to the surface of the crystal. We have one-dimensional defects, edge dislocations, screw dislocations, two-dimensional defects, surfaces, grain boundaries, twin boundaries, tilt boundaries, etc. Three-dimensional defects, voids, cracks, stacking faults, etc. Now, when we talk about non-crystalline solids, amorphous structures like glass, there is no lattice to describe. So instead, we have the distribution of atoms relative to a reference atom, and this distribution is given by a radial distribution function. So if I call the concentration of atoms at a distance r in a spherical shell between r to r plus dr, n of r dr, n bar of r for all atoms is the average concentration of atoms at a distance r from a reference atom. So this dr basically goes to 0, and we have at a distance r specific location we have an average concentration of atoms. Now if I multiply the average concentration of atoms with 4 pi r square, I get the radial distribution function. So that's the surface of the spherical distribution. And this radial distribution function will have delta functions wherever we are at a lattice side. So this is going to be, for example, 1 lattice constant, 2 lattice constants, 3 lattice constants, etc., going away from the reference atom at r is equal to 0. However, if we have the radial distribution function proportional to r square, so it's 4 pi r square n bar of r, this implies n bar of r is a constant. So when would that happen? When you have a completely random distribution, you would have this parabolic behavior. If you have a parabolic background but you have some peaks and dips, then that's more realistic for an amorphous structure. There may be some short range order that's locally in the solid, basically. Okay, so for amorphous structures, we are talking about the radial distribution function, and truly random distribution would require the radial distribution function to be proportional to r squared, because the concentration of atoms at the distance r would be a constant from a reference atom. And for a more realistic case where we have some short range local order in the amorphous structure, we would see this random distribution background with some peaks and dips